So I'll try to keep it to minimum, and our minimum is really a minimum. You know, it's much more minimal than Landau's theoretical minimum. We'll do it only for rotation, which is an abelian group is one parameter. So this is a baby group. You know it as Fourier analysis. So this is the baby group of all groups. And even that will require thinking. So there is a definition of Lie group, and I will not say what it is. It's read it once. We'll never use any part of what I said in this definition. And for us, the important thing is that when we look at the group element of our group, it's parameterized by some parameter, typically angles or distances if you're translating things, if you're sliding and rotating. So these parameters, of which in general there is some number, tell you if you were here where you end up after group rotation. And it can be any place on the manifold, group manifold. And whenever you have something continuous, then our definition, we did it for time before, we define transformation along any trajectory in time. We discovered that natural thing is to go small steps in time, and that gives you some kind of time-ordered integral. So the natural thing is to write any such continuous transformation as exponential, this being lots of product of lots of steps being Euler's definition of exponential. And in this exponential, there are two things. There's something called a generator. I'll give you trivial examples to see what they are. And then, so that tells you I will move in this direction. So in general, a group operation is D by D matrix. If I'm in a state space M of dimension, so if I specified my state by D numbers, then what the group transformation has to do, it has to change all of them, or subset of them. In general, all of them. So this is a D by D matrix. And now this matrix can always be written as exponential of some other matrix. That we have no problem with. But the clever thing about this other matrix is that that splits into two parts. This is a parameter. So this is very much like here, when we looked at Jacobian, which is a linear matrix, you know, moving linear neighborhood of trajectory, we wrote here time-ordered e to the time integral d tau of our deformation at the given instant in time. So we have this parameter. And if this happened to be a constant matrix, then we would write it as t from 0 to t times the constant matrix. So this is the same story for symmetries. And there is one of these constant matrices, but we will only do rotation, so you'll only see one in our examples. But in general, there's some bunch of them. And this number tells you how far you went in transformation. So if this number is very small, you can think of this as 1 plus phi t plus order phi squared. You can always expand this Taylor series. So this is just a representation of your transformation, which enables me to put continuous parameters in a natural way, just like we did it for time, so it's not so strange. And then the important thing we knew about the time is that the reason why we had to call this time order product is because in general these matrices did not commute. So as we went around, this local shear matrix or stability matrix was changing, and it didn't commute with anybody before or after, so I had to write it this way. Now Lie groups are much nicer, the kind of compact Lie groups that we'll study here. They have a property that this vector which generalizes this shear, this transformation matrix is same every place. So the law of rotation is same every place. So these guys are constant matrices, but if there's some number of them, I would have to worry about how they commute, and that's called non-abelian Lie algebras, Lie group. So what have we gained by this? See, this is infinity of matrices. So G, element of group, infinitely many. Because, you know, I can rotate like this, or I can rotate like this by, you know, milliradian. So there's infinitely many possible rotations. But T, which are the laws of motion for the group transformation, they play same role that velocities play for time. There are few. So the cardinality, or the number of these matrices, linearly independent ones, number of linear independent, we'll call it n, is finite. And for these lectures, n equals 1, to make it even very simple. So you have traded in infinitely many matrices for a matrix and a parameter. So that's why you do this. And you have to do this anytime you have continuous deformation of anything. Time evolution, you know, you do this, and in group deformation and general relativity, do something else, but this is always the idea.